we're going to look at an interesting function, y equals 1.1 to the x divided by x to the 10. So what's this? This 1.1 to the x, it's just an exponential. It's just like, a to the x, some number a, or e to the x, right? So this is just an exponential on top of what's on the bottom. Well, this is just a polynomial, right? So the form of this function is an exponential over a polynomial. And let's try and graph it, okay? The first thing that I notice is that in the domain, x cannot equal 0. Okay, so we know that there's a vertical asymptote at x equals 0. Something else I notice is that x to the 10 is always positive, just like x squared is always positive, and also an exponential is always positive. A to the x or e to the x is always positive. So from that, I get that y is greater than 0. So if we were going to graph this function, we know that it's in the upper half plane and that the y-axis is a vertical asymptote, okay? So something else that I would use to sketch this is I would look at the limits. I would say as x approaches minus infinity, as x approaches 0 from below, as x approaches 0 from above, and as x approaches infinity, in each case, comma, 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 what is y approaching? Okay, so in the first case, as x approaches minus infinity, so out at minus infinity, what's y doing? Well, 1.1 to minus infinity, think of an exponential function. So an exponential function, increases up like this. So at minus infinity, we're over here. So the exponential function is doing something like that. We're at 0. So this is going to 0. And what is x to the 10 doing at minus infinity? Well, minus infinity to the power of 10 is a huge number, so it's going to infinity. So a tiny number divided by a huge number is 0, right? So the function is down here at 0 somewhere out at x being close to minus infinity, okay? Now what happens as x approaches 0 from below and from above? Well, from below, when x approaches 0, what does the exponential function do? It cuts at 1. So this is going to be like 1 over, and what does this do when x goes to 0? Well, it goes to 0 itself. 0 to the 10 is 0. So what's 1 divided by smaller and smaller numbers? Well, it goes to infinity. Note that everything's positive, right? So this can only be positive infinity, not negative infinity. And what happens when x approaches 0 from above? So from below it went to infinity. From above, well, exactly the same thing happens, and you can have a think about that if you're not convinced. So from when we're approaching 0 from above, we're also going to infinity. Okay, so you can probably, at this stage, I'm going to tentatively fill this part of the curve in and say our function looks something like this. Now the last bit, as x goes to infinity, and this is what's going to cause us some trouble. What's 1.1 to the infinity? Well, an exponential function looks like that, so it's at infinity, we're going up to infinity. So this looks like infinity divided by, what's infinity to the 10? Well, infinity to the 10 is infinity. And this is where we run into our first problem, because depending whether the top or bottom is approaching infinity faster will determine what happens. Basically, we could have 3 cases. If they both approach infinity at the same time, we could go to a constant. If the top one approaches infinity faster than the bottom one, then this just keeps getting bigger and bigger and we go to infinity. But if the bottom one approaches infinity faster than the top one, then we're dividing by bigger and bigger numbers and we go to 0. So which of the 3 cases is the answer? Well, let's just look at these. You could be forgiven for thinking that basically this bottom one's going to dominate, because x to the 10 sounds like it's a lot bigger than 1.1 to the x, right? This is a tiny number. This is a pretty big polynomial. So let's assume that this is correct, right? And let's say that this one goes to infinity faster, which means the function goes to 0. Okay? If the function goes to 0, then our graph is going to go down to 0. And, maybe this is our graph. Okay. What I did was I went to a website, Wolfram Alpha, to check what this function looks like. And upon first inspection, I got this graph, which looks like we're correct, right? So obviously the scale is very different, but there's that blue line there. That's the branch that we got over this side, and the blue line on that side. There we go. We could be, it looks like we're correct. Just to be very clear, I'll say that we're not correct yet, and there's more to this story that we haven't seen yet. But it looks like what we did was correct, okay? But what I'm going to do is I'm going to do a little bit more work using calculus, okay? And the way this is going to work is I'm going to take the logarithm of both sides of the function. So I'm looking up here and taking the log of both sides. So I get log of 1.1 to the x divided by x to the 10. And now what I'm going to do is use implicit differentiation to differentiate that. Okay? So if maybe before I differentiate it, I'll use some log laws to simplify this. Okay? So the logarithm of a quotient is the difference of the logarithms. So I'm subtracting log of x to the 10, and basically what I get is log of y equals, using again the log law, I can bring this power down out the front. So x log 1.1 minus 10, I'm bringing this power down the front, log of x, and now I can use implicit differentiation. So I differentiate both sides, and I get, how do I differentiate log? I get 1 on the argument, but times dy dx is equal to, how do I differentiate this? Well, log of 1.1 is just a constant, so this is like ax. How do you differentiate ax? You just get a, or you just get log of 1.1 minus, how do I differentiate log? It's 1 on x, so this becomes 10 on x. Okay, now I multiply through by y, but I'm going to write in what y was. Y was this thing, 1.1 to the x over x to the 10. Okay, so that's the derivative of this thing. dy dx equals all of this stuff times this. Okay, and what was the point of finding the derivative? Well, I noticed straight away that I can make the derivative 0 by choosing an appropriate value of x in here. I can't make any of this 0, but I can make this factor 0. So basically what I get is that dy dx equals 0 if x is equal to, basically if I make x equal 10, then this becomes 1, but I don't want to subtract 1, I want to subtract log of 1.1, so I need to put log of 1.1 in the bottom. So if you substitute this value of x in here, you will get 0 here. So dy dx equals 0 if x is equal to this, which by the way is approximately equal, if you do it on a calculator, to 104.92. So that's a bit odd. Why? Because what this is basically saying is that there's a stationary point on our graph, not a 2, but way out here at 104.92. Okay, so something's happening at 104.92. So I went back to Wolfram Alpha, and this time I graphed the function from, so that I captured this x value. I went from 104.91 to 104.93. Okay, so this stationary point, we don't know if it's a maxima or a minima, or if what it is. It's just a stationary point right now where the derivative 0 occurs within this graph. And if I look at the graph that I got, I actually get this minima. So look, it's the same function, 1.1 to the x divided by x to the 10, and it turns out that at 104 there is a turning point here. Okay, so I'm starting to think that this graph up here is wrong. So that this thing here, our first choice, was wrong because that graph is wrong. Okay, so maybe as a second guess, I'm going to rule out constants straight away because these are different types of functions. So for them both to approach infinity at the same rate, would be very odd, right? So I'm going to rule out the constant, and I'm going to look at the top case. In the top case, we said, okay, what happens if this function, as small as 1.1 is and as big as 10 is, what if the exponential still dominates the polynomial? Okay, what would happen then? Well, if we try to draw the graph of this branch stays the same, that one stays the same, but this time instead of going to 0, it would go back up to infinity, and the only way we could sketch it is with having this turning point. Okay, so if I'm going to say that this is correct, and this is what our function looks like, you know, how does that compare to what Wolfram Alpha says? Well, Wolfram Alpha, you know, said this up to 2, but we need to go all the way to 104 to actually see what's going on. So after I graphed that one, and then I graphed this one to check what's happening at 104, I then graphed the function, the same function, from minus 300 to 300. And finally we get a good picture, because if we look at the function now, we see we do indeed get that same shape on this side all the way out to minus 300, and we do indeed get this shape here where the function is coming down at about 104, reaches the minima and then starts to climb, and you see at about 200 it really does start to shoot off. Okay, so obviously the graph that I drew up the top is to a very different scale to this accurate graph, but really, you know, just looking at the function, this would be suitable as a sketch of it. Okay, so basically the take-home lesson from this video should be that when you're looking at limits, an exponential dominates a polynomial. Okay, and so that's, you know, that's true for, even if instead of y equals 1, you know, if I put 1.001 divided by x to the 1000, this would still be true. It would just mean that we'd have to go further and further along the x-axis before the function picked up again, and sorry, that was to the x, and this factor started to dominate this factor. Okay, but finally, maybe as a now as an example, you could perhaps look at this function, y equals e to the x, so an exponential just like this, divided by a polynomial. Well, what's a good polynomial? What about x squared? Maybe I'll just write all of that here. E to the x divided by x squared. And, you know, just looking at this function and now this function, really they're exactly the same form. We've got an exponential divided by a polynomial, an exponential divided by a polynomial. Try and graph this thing, look at this thing on Wolfram Alpha, and see if you get something similar to this plot. Okay. One last thing is I'll put the links to the Wolfram Alpha pages that I used to get the 3 graphs in this video in the description of this video, so that you can perhaps, you know, play with changing the ranges yourself.